x, and the distribution of x satisfies Kolmogorov-Fokker-Planck equation, or KFP for short. Sometimes I will say just FP for Fokker-Planck. And I refer to this type of equation. You see that alpha is involved in the drift, which is involved as in the transport term for this Kolmogorov-Fokker-Planck equation. And here we have an initial condition. So this is really a forward Kolmogorov equation. If I want to stress the dependence on the control, I will use a superscript alpha for x and for m. All right, so this is just for the dynamics. Now the question is, what is the player trying to optimize? So typically, the player has a running cost, f, which is a function of t, xt, alpha t, and also mt, the distribution at the current time. I have discussed this morning the, let's say, regularizing interaction type, non-local, but regularizing, or the local interaction type through m at exactly xt. So you could imagine models of crowd motion. Actually, I will present that in the next lecture. Models where maybe you interact through the density of agents around you. So then you put a kernel and you take the convolution of the density with this kernel, or maybe you interact with the density exactly at your location. And you have two types of interactions, modeling more or less the same effect, but in one case, you have a non-local dependence, and in the second case, a local dependence. So then we had this cost function. There is also a terminal cost. And when the player tries to optimize this, the player ends up having a Hamilton-Jacobi-Bellman equation, or HJB for short, to solve. This equation depends on the mean field flow. So I will stress this again because it's really one of the key difficulties. If you take a standard optimal control problem, you don't have this MT here. Usually, if you take an optimal control problem for a single agent, you don't have MT. You try to control your state. You have the Hamiltonian of the system, and this gives you the HJB equation, which is a backward equation starting from a terminal condition. Now, because there are mean field interactions in your cost, you need to know, if you want to solve this HJB equation, you need to know the mean field term. So if someone gives you the evolution of the mean field for free, then you can solve this HJB equation, at least if you have numerical methods to do that. But the question is, how do you find the mean field flow? Well, it solves the equation I gave before, which is the Kolmogorov-Fokker-Planck equation. And so you end up with a coupled system, forward, backward. So again, this warning that there are different conventions. So the one I'm using here, the Hamiltonian, is the max of the negative of the Lagrangian, but you can use other conventions. Just be careful with the sign in the PD. All right, so how do we recover the optimal control? Imagine you have solved the HJB equation. You can recover the optimal control, which is in fact the equilibrium control in a mean field game, by taking the argmax. So if you are at time t, and position x, you plug this in your Lagrangian, and for the adjoint state, you use the gradient of the value function, gradient of u, and this gives you, and you take the argmax. So you take the action that maximizes your the negative of your Lagrangian. Here, actually, there should be one extra argument. This would be for a standard control problem. Actually, there should be one extra argument, which is m at time t. Why? So because if we go back to the definition of the Lagrangian, here you see that the Lagrangian depends on m, because m is involved in the running cost and in the drift. So I will correct this typo and upload a corrected version of the slide, there is empty in the Lagrangian. And because of that, and because empty is also present in the AJB equation, in order to compute the optimal control, alpha hat, I need to know empty and the gradient of UT. I need these two ingredients. And how do I find them? Well, I find them by solving the forward-backward system. And once I have solved this forward-backward system, so you see here there is no alpha anymore. I have replaced alpha by its expression in terms of the Hamiltonian. Then I can plug this in the argmax, and I can compute alpha hat. So we have this forward-backward system, and now the goal is to solve this forward-backward system. At least when we use this path of using the PDE system, there is another direction, which is the SDE system, and then some other directions. But if we focus on PDEs, then the goal is to solve this forward-backward system. So in the next lecture, I will explain how to discretize, different ways to discretize this PDE system. But for today, or this afternoon at least, I would like to focus on a simpler setting where we only need to discretize time and we don't need to talk about discretization of space. All right, so some exercises I mentioned earlier. You can try to take these examples where you have, let's say, the linear quadratic system, for example. So we are going to come back to this. Not exactly this setting, though, I changed a little bit, but you can try with this one. There is a congestion example. So let me say a few words on this. You see that the drift is just equal to A. So actually, that's the example I have most often in mind in these lectures. The drift is A. So what does it mean? It means that, it means that dxt is equal to alpha t dt plus sigma dwt. In other words, the agent controls his velocity directly. So you control how you evolve, but there is some perturbation in your dynamics. All right. And the cost, here I call it congestion. So what does it mean? It means that you pay, so this is a running cost, meaning this is a cost you are going to pay at each time t. Here you see a quadratic term, meaning that if you take an action with a very large norm, so in other words, you try to take a very high velocity, for example, you try to drive very fast or you try to walk very fast, then the cost increases. It increases in a quadratic way. So this means that you are not going to move very fast, except if it brings a very high reward later on. Maybe you can reach an interesting position, and so you want to walk very fast, but otherwise you try to avoid walking too fast if it's not necessary. And moreover, this term is multiplied by m of x. So here I'm assuming that m is a density, smooth enough, etc. And I take m evaluated at x. So this means that I pay a quadratic cost to move, depending on my velocity. And this cost is multiplied by the proportion of people at my location. So if I try to go fast in a region where there is nobody, then m of x will be almost 0. So take the extreme cases. If m of x is very close to 0, or if m of x is large, let's say small. So small means close to 0. So it is small if there is a low density. Low density at my position or at my location. If there is a low density at my location, m of x is small. So my cost to move is multiplied by a small coefficient because I can move fast and pay a relatively small cost. But if the density is large, then I pay an even higher cost to move. And so this should somehow discourage me from spending too much energy in very crowded region. So I will call this congestion in these lectures. I mean, it's not just me. It's, in fact, I think Pierre Williams discussed that in his lectures several years ago. And so the idea is that you pay a high cost to move in a crowded region. If you don't move, though, you don't pay any cost, right? With this f, it's a squared multiplied by m of x. If a is equal to 0, you don't pay any cost. The second one is slightly different. I mean, the last one, here the third one is aversion. And what I mean by that is that you pay a cost for being in a crowded region, even if you don't move somehow. So you see here, it's an additive dependence. You pay a quadratic cost to move, no matter what. And you also pay a cost for being in a crowded region. So if m of x is large, you don't feel comfortable, and you pay a high cost. That's the intuition. So these two have, sometimes they have similar effect. Maybe you will see some kind of diffusion of the mass because agents will try to avoid crowds. In the first case, it is because they don't want to go through a crowded region. And in second case, it's because they don't want to stand in a crowded region somehow. So numerically, maybe we will see some similar effects, but it's not exactly the same thing. And in some cases, they can be pretty different. So I will leave that as an exercise. In fact, I will come back to this later in the next lecture, but for now it's an exercise to try to write the PDE system in these three cases. Another exercise, try to derive the optimality conditions for the social optimum problem. And in fact, I will answer to this question right now. So the social optimum problem, which I discussed mostly in the static case, here is a form it takes in the dynamic case. Sometimes it's called mean field control or mean field type control, sometimes control of Makin-Vlasov dynamics. So why Makin-Vlasov? Because we have the law of x in the dynamics of x. So you could say, well, this was already the case, but not really. So if I go back here, you see that what I plug in the dynamics is empty, and empty is not yet the law of x. It should be the law of x at equilibrium, but when the player tries to solve the optimization problem, empty is given to him, and he tries to solve his optimization problem. So the evolution of x is not really Makin-Vlasov here. It is Makin-Vlasov at equilibrium, but not during the optimization. When we look at I will refer to this as mean field control because I have to choose one of the two terminologies. So I will call this mean field control, and I will write MFC for short. It's similar to MFG. You see that the definition of the cost is pretty similar, except that what I plug here is M controlled by alpha. And so in particular, the cost of JMFC is a function of purely alpha. I'm not fixing a mean field flow and solving an optimization problem. I am solving an optimization problem in which the mean field flow is controlled by alpha directly. So this is really, it corresponds to the idea is that all the players in the population are using this control alpha. So if I change alpha, I change not only for the representative player, but for the whole population. And so this has an impact on the distribution. So there are several approaches to design or to derive optimality conditions. One is a dynamic programming approach. Once you view the problem as a problem for the distribution. So if you try to view this problem as a problem for xt, you will not manage to write a dynamic programming principle. And so the value function here should be a function of t and m at time t. So you see that because mt is a probability distribution on RD, the value function is defined. It takes an input which is infinite dimensional. This mt is infinite dimensional. So you can write a dynamic programming principle with a backward equation, backward PDE for V. Now, can you solve it numerically? It's not so clear because the input is infinite dimensional, but at least mathematically, you can write a dynamic programming principle. Another approach is to use calculus of variations, again, taking M as a state. And so here, if you view M as a function of t and x, the adjoint state is also going to be a function of t and x. This is similar to the case where you have an ODE, let's say you control an ODE in dimension d, then the adjoint state is also in dimension d. So here you try to control, let's say, a function of t and x, and the adjoint state is also a function of t and x. And a third possible direction is to use Pointryaghin's maximum principle. This is a part that I more or less skipped at the end of the previous lecture, or I went very quickly, but we will come back to this later on. And here it's again a maximum principle. So there is an adjoint state, but the adjoint state is stochastic, and it corresponds to x, actually. So I see there is a question. I didn't understand how MT is not controlled by alpha since the drift depends on it. Okay, yes, thank you. That's a good point. So I imagine your question refers to this slide. Here there are two things. So it's true that what I write here is MT controlled by alpha. So you are right. This M would be controlled by alpha, and I would denote it M exponent alpha or superscript alpha. So this one, yes, absolutely. But if we look at the definition of the problem, which maybe I should have recalled somewhere, but let me recall it here. If we look at the definition of the cost in a mean field game, I would have the control alpha for the player and a given mean field flow. So this would be given to me fixed, and I try to find the inf over alpha. So this would be the best reaction to a given mean field flow. And in a second step, I would say, well, actually, M should be M of alpha. So this would be one part. And the second part is that M should be equal to M of alpha. So maybe let me be more precise. So here what I mean is that I am looking for a pair, alpha hat, M hat. And I say that this is a mean field Nash equilibrium, or just Nash equilibrium, because I will always talk about mean field now. If when I look at this, I have the optimum by playing alpha hat, and second of all, M hat should be equal to M controlled by alpha hat. So what I was trying to say before is that in the definition of a mean field game, we really split the two steps. And during the optimization, I don't know yet, in some sense, I don't know yet that M hat is controlled by alpha hat. So this is different from the mean field control problem, which is inf over alpha, J alpha. And here I immediately plug M alpha. If I do this, you see that during the infimum, I am changing this alpha and this alpha at the same time. Whereas in a mean field game, I'm only playing with the first alpha, which is for the representative player. And in a separate step, I say that M hat should be M controlled by alpha hat. All right, so let me read out the question, but the M given will be generated through a choice of alpha algorithm. Yes, I agree. So indeed, as a second step, like this, but I hope this can, let's see. I think the key point is this, the fact that the two problems are different. If I minimize over alpha and I plug alpha, I use alpha both for X and also for M, it means that when I am changing alpha, I change everything, X alpha and M alpha. Whereas in the first type of problem on the left, I am changing alpha. I am trying to optimize over alpha, but M does not change. Okay, thank you. So this is really a subtle point. So I mean, once you see it, I think it becomes clear, but it's really not that trivial why the two problems are different. And really the key point is, what do you do with M? Do you control it with the same alpha immediately, or do you say later on that it should correspond to M controlled by the same alpha? But doing it later on means you are doing some fixed point problem. Okay, so if I go back to the mean field control problem, now maybe you see that actually X alpha here is involved, but only through the expectation. So here I could rewrite everything in terms of M alpha. In terms of M alpha and without X alpha. So I can get rid of X alpha, I mean virtually, because I need X alpha only through its distribution. So basically what I can do is I can write the integral between 0 and t of the integral over Rd of f x. I will write alpha tx. I will write mt alpha, and then I write mt alpha dx and dt. And by doing that, what do I gain? Well, I don't need X alpha anymore because I just need the expectation of the cost, in fact. So the expectation is the integral with respect to the law of X, which is precisely M alpha here, because we assume that we are controlling the whole population with the same control. And if you do that, you rewrite the cost just in terms of M, and then you can derive a value function or an adjoint state U. The reason why I insist on that is because I'm going to use this. I'm going to write the PDE system. I'm just going to give it immediately. I'm not going to justify, but I can provide references for that. And this adjoint state little u is not the value function. So from the point of view of interpretation, it's important to realize that the value function for the mean field control problem is not the same thing as the adjoint state little u, for which we are going to write a PDE, but this PDE, which looks like an HJB PDE, is not, the solution is not really interpreted as a value function. So here is a PDE. I just give it to you directly. Here, as I mentioned before, same thing, there should be MT here. Sorry for that, I will correct it. And the forward equation is the same, but the difference is in the backward equation. So the backward equation has two extra terms here and here, which correspond to the derivative of the Hamiltonian and the derivative of the terminal cost with respect to M. Intuitively, if you are familiar with calculus of variations, the idea is that in a mean field game, when I change the control, I do not change the distribution. So I will not see any derivative with respect to the distribution. But in a mean field control problem, when I change the control, I change the distribution. And so I should see some derivatives of the cost, of the drift, of the terminal cost with respect to M. And that's why these terms appear in this backward PDE, which is for the adjoint state little u. What do these derivatives mean? So there are several definitions of, how to derive a function with respect to a measure. In particular, there is a notion of, so we can call it Lyon's derivative, and it's also used in optimal transport and gradient flows, etc. And Lyons has proposed a new interpretation of these derivatives and really developed a lot of theory and applications in the context of mean field games. So you can find a lot of details in the book of, again, François Delarue and René Carmona on this. But the notion I'm going to use here, this would be a bit more complicated to explain. So I will use it later, but for now, I use a simpler notion of derivative. I assume M is an element of L2. It's a density in L2 of Rd. And then in L2, I can take somewhat standard derivatives. And here is the notation that you can see at the bottom. And if you want more details, you can check the book of Ben Soussan, Freze, and Yam. the idea is you do a perturbation of M in the direction M tilde. So you take two elements of L2, you do a perturbation, and what you obtain is the integral of, so you can use a product notation if you want. This would be, you can interpret it like this with respect to M tilde. And this is the function that you have inside is the derivative. It is a function of x. And you can integrate it with respect to M tilde. So I'm going to use this notion, just one word of caution here. So you see that here xi is a variable of integration, and I have xi and xi here. But in the PDE, xi is a variable of integration. I have xi here, but then xi is inside the function, and here I have x. And same thing here, I have xi and I have x. So at some point there is a Fubini, and that's why you end up with xi inside the function and not in the outer part. For the sake of time, I'm not going to explain all the details here, but again, I'm happy to answer questions if you check this reference, and they provide the detailed derivation of this PDE, at least formally. So now, this is valid beyond the linear quadratic setting, this PDE system, and same thing for the mean field game system. And what I'm going to do is I'm going to specialize this PDE system in the linear quadratic case, and then solve it in this linear quadratic case. I don't know if there are any further questions for now. All right, so let me continue. Linear quadratic setting. So compared with the exercise I gave earlier, I take a slightly different setting, but you could apply the same strategy to the previous one. So the one I'm going to consider here is this one. The drift is a linear function. For simplicity, I will mostly focus on the case of dimension 1. But here, in general, you would have x in dimension d. Okay, so this x is an element of Rd. M bar, which is a mean, actually it's given here, is an element of Rd. And the action could be an element of Rk. It doesn't have to be in the same dimension. Then A bar, and B should be matrices of suitable dimensions. So in particular, A should be d by d, because for the drift, I need to end up with a vector of dimension d, and B should be d by k in that case. The running cost and the terminal cost are quadratic in the same quantities. So here I take x transpose x. I take this term for the mean field interactions. I will come back to this, and A transpose A here, multiplied by some matrices inside. So if we look at this term here, which is a term of interactions, basically, let's imagine that S is equal to just identity, for example. And let's take just the dimension. Let's imagine that maybe Q bar is equal to identity as well, or let's do just the case of dimension 1. D is equal to 1, take S is equal to 1, take Q bar is equal to 1. Then in this case, we end up with X minus M bar squared, meaning that you pay a high cost if your position is far from the mean position. So if you want to minimize your cost, you should try to be close to the mean. But of course, you also pay a cost to move. Okay, so imagine you are far from the mean, you want to get closer to the mean, you have to pay for that. You have to pay some cost a squared or something proportional to a squared. So you will try to get closer to the mean, but without paying a very high cost for moving. And so you have to balance all of that. So, okay, I mentioned at the beginning that typically is a case where all the agents try to follow the group. You may have some failure of uniqueness of Nash equilibrium, because basically, if you remember, this was maybe in my second example, at the very beginning, the static case, if everyone wants to be at the same place, then, well, any place could be good. And just as long as you are with the group, you are happy. And then, well, you have as many Nash equilibria as possible positions. So no uniqueness. But here in this setting, we are going to have, under some assumptions, uniqueness, even though you try to follow the mean, but because you have an initial condition, you have some cost to move. You also have the first cost here, which is basically attracting to 0 in some sense, because x squared should be close to 0, at least if you take q equal to the identity, for example. So then, because of all of that, we may still hope to have uniqueness. And existence as well. So the interactions are only through the mean, and the drift is linear, cost is quadratic. And the key point, as I'm going to illustrate next, is that in this case, the mean field game equilibrium can be computed just by solving ODEs, and we don't need to solve PDEs. So I think it's a good example to illustrate some ideas before going into more complicated arguments. So why is that? Why is it that we just need to solve ODEs? What do I mean by solving the mean field game equilibrium? Maybe just one word on this. What do I mean by the mean field game equilibrium? What I mean mostly here is the optimal control or the equilibrium control. I will use hat for mean field game, Nash equilibrium, and I will tend to use a star for social optimum. So hat here means, alpha hat means the equilibrium control. And we also want to have m hat, if possible. But this will not be completely guaranteed. What we are going to get instead of m hat is m hat bar, the mean. We are going to get the control for sure. And we are going to get, so as a function of t and x, and we are going to get the mean of the distribution, not necessarily the whole distribution. Maybe for this, we need extra computations. So let's go back to the AJB equation and take the case d is equal to 1. I'm going to go through the details because I think it can be useful in many situations, again, as a benchmark when you want to test an idea, whether it is about the theory of mean field games or whether it is about numerical methods. I think this linear quadratic setting is really helpful. So I want to go through the details, but I will go a little bit quickly so you can check again later and think more about whether everything makes sense. So I take the Hamiltonian defined previously. The Lagrangian in this case is obtained by taking the running cost and the drift multiplied by p. I take everything in dimension 1, so I drop the transpose. I want to simplify the notations, alleviate the notations. And so I have these expressions. The optimal control is given by the minimizer of the Hamiltonian here, as the maximizer, sorry. So I use first order optimality condition, and I find that A is given by minus B over C times P. So in general, you see that the maximizer here would be a function of X, M, and P. But in this special case, it depends only on P. So that's nice. What is P? Later on, P is going to be replaced by the gradient of U, the gradient of the value function. So intuitively, what we have just said is that when you are at time t and position x, what you should do is you should use the gradient of your value function multiplied by minus b over c and use that as your action. So in other words, you follow the negative of the gradient of the value function, which makes sense because we want to minimize. So when you see that the value function is increasing, you say, well, I go in the other direction somehow because I want to minimize in a very hand-wavy style. Now, we go back to the Hamiltonian. We plug the expression for A, the optimal A. And so we end up with an expression here after simplification, which does not depend on A anymore. It depends only on X, M bar, and P. We compute in particular this HP here, which is, what is HP? It is the derivative of the Hamiltonian with respect to P. So you notice that the Hamiltonian is a polynomial of degree 2. You take the derivative, you end up with a linear function, linear in P, with some coefficients that depend on X and M bar, but fine, in terms of P, it is a linear function. So why did I compute HP? Because I want to plug it. I want to plug it in the AJB equation. So if you remember, oh, sorry, I will need it later on for the Kolmogorov-Fokker-Planck equation. For now, for the AJB equation, I only need the Hamiltonian. So you may notice that this long expression here is just the Hamiltonian, the expression I obtained here, but I replace P by gradient U at T and X. And the terminal cost, I have the expression which is given by G, which was a function of X and M bar at time T. All right. So now we have this PDE. What can we do? I say that actually to solve this PDE, we need only to solve ODEs. So how is it possible? Because here we have a PDE for the function of T and X, but there is a classical trick for linear quadratic optimal control problems, and we can apply the same idea here, even though there is a dependence on M bar T. But if you want, M bar T is just a parameter, right? So M bar T here appears as a parameter in my AJB equation, but it's a function of time, and it's here, and I'm trying to solve the AJB given this function of time. So it's just one of my coefficients somehow. So the idea is to look for U in the form of a quadratic function of X. So we make an ansatz, which is we make a guess somehow. We look for U in the form 1/2 PT X squared plus RTX plus ST. This P has nothing to do with the previous P. So this P here is the one that comes from here. It is not related to the P that was the argument of the Hamiltonian, except they are both related to the value function. But the notation is for this slide. So what do we get from this expression? Well, you take this ansatz for U, you compute the time derivative, you compute the gradient, you compute the Laplacian, and you plug all of this back in the PDE. When you do that, then you obtain a long expression which involves P, R, S, as well as their time derivative. So P is a function of time only, something for R and S. So you have a time derivative, and what you obtain is an equation for P, R, and S. And we will be able to identify these coefficients later on. The second remark that I want to make is that the dependence on M is only through M bar. So actually, we are not going to solve the KFP equation. We are going to solve the equation for the mean only. So how do we do an equation for the mean? Well, you take this PDE here, you multiply by X, and you integrate over RD intuitively. And if I do that, I get dm bar over dt. The second order derivative disappears. I get the divergence. I integrate it, and I have this integral of m times hp, which looks a bit complicated. But if you use the expression of hp, and if you use the expression of gradient u, which is given above, then you can get this nice simplification here on the right, which depends on m bar t only, as well as pt and rt, but there is no integral anymore, except just the mean. So we have got rid of the Kolmogorov-Fokker-Planck PDE, because now we have an ODE for the mean. Okay, so if I write this, I get that m bar dot, if you want, the time derivative is equal to exactly the minus the term minus or no minus, so it's equal to exactly this here. So I have an ODE for the mean, but you see that this ODE involves PT and it involves RT. So I'm going to need to compute PT and RT. So we end up with the following consequence. The mean, I will denote it now by m bar superscript alpha hat, because it is really controlled by the equilibrium control. I will denote it by ZT. So ZT is just a shorthand for m bar alpha hat t. And I'm going to write an ODE for ZT. Alpha hat itself is minus b over c times the gradient of u. So let me repeat this. This is the gradient of u at t and x. And the value function is given by u of t and x. So in particular, if I want the total expected cost, what do I get? I write u at time 0 at position x, and I need to integrate this with respect to m0 dx over rd. All right, but this m0 is going to be given in my model. It may be Gaussian or maybe not, but I have it in my model, and u0x is going to be given by just 1/2 p0 x squared plus r0x plus s0. So if I have solved the ODEs that I'm going to present next for PRS, then I have the value at time 0. So what do these ODE look like? And I'm not going to, so here I'm skipping some computations, but they are based on the principles I described before. You end up with an ODE for the mean, which is the first one. It's a forward equation because you start from time 0. And then you have 3 backward equations here, which are obtained from the AJB equation by identifying the coefficients in x squared, the coefficients in x, and the coefficients of order 0. So we have these 3 ODEs. What can we say about it? I'm not going to analyze this ODE system, but once again, it is a forward-backward system. So you see, we have gained in terms of dimension. We don't need to compute functions of x. We have reduced everything to ODEs, but there is still the difficulty of forward-backward structure. And that's why I'm going to use this to illustrate several numerical algorithms that we will use later for PDEs. But the ideas will be pretty similar once you understand the main ideas. One comment related, so previously I said that once we solve this ODE system, we recover the optimal control. So imagine we solve this, and I'm going to explain that right now. Then you go here and you get the mean, you get the optimal control or equilibrium control, and you get the value function. I don't claim that you get the distribution. Why? Because it depends on the initial distribution. What you get for sure is a mean, but if M0 is Gaussian, so if M0 is equal to a normal distribution with mean mu parent sigma, then can we get M at time t for any t, or M controlled by alpha hat? So one answer is yes, we are going to solve the KFP equation. We can plug the gradient of u in the KFP equation, and we can solve this PDE. So yes, can we do it without solving the PDE? And actually, yes, we can in this case. Sorry, so this is an equality. M at time t is a normal distribution with mean, actually, this is what I denote ZT. and variance sigma t. So here I didn't express it, but you can also get an ODE, or you can get an expression for sigma t, and then you have a full characterization of the distribution at time t. If M0 is not Gaussian, then it's not so clear. It's not so clear that you can get MT alpha hat using only ODEs. Maybe you need to solve the Kolmogorov-Fokker-Planck PDE if you want the full distribution. All right, any questions so far? No, everything is perfectly clear, hopefully. All right, so now, linear quadratic mean field control, you can apply the same strategy. The only difficulty is that you have one extra term in the AJB equation. So we need to understand this extra term, which was an integral with respect to m of the derivative of the Hamiltonian. So let me compute this derivative explicitly in this case. I take the definition, so I say, well, my Hamiltonian is a function of x, m, and p, and I do a perturbation of m. This is exactly what would happen if I was trying to control m and changing the control. I would do a perturbation of m. So let's see what happens. In this case, Hamiltonian is quadratic in m, so I get the expression on the right. This means I take the derivative with respect to theta, and I evaluate that theta is equal to 0. In that case, I get the expression on the right. But I really want to use my definition of partial m h. I want to make this term appear. So if I want to do that, I have to make appear an integral with respect to m tilde. So that's why I rewrite the first line as a second line. And in that case, somehow artificially, I write it as an integral with respect to m tilde. I'm not cheating because I'm just writing the expectation. So this is really the integral of xi m tilde xi dxi. And I'm putting everything inside this integral, even though it does not depend on xi. So by definition, if you go a few slides before, by definition, we have identified this derivative. It is this expression. Now you remember that I made this comment. In the PDE, we need to swap the role of x and xi, actually. This is due to the derivation of the PDE, the way we derive it. So we swap x and xi, we take the integral of dmh here, and then we do the computation. So if you do the computation, you replace the gradient of u by its expression. And here I'm going to use a similar form for u, except that I put a check or a hat inverted. So a check on P, R, and S to distinguish from the mean field game case. But it is still a polynomial of degree 2. So if you do these computations, you end up with an expression here for the extra term that appears in the AJB PDE of mean field control. And this term here, it does not involve xi anymore because I did the integral, but it involves m. So here, all right, I'm mixing some notation. So I should probably put a t below everywhere just to be clear, mt here, just to be consistent, because I have a t in the gradient of u. But anyway, I have only the mean of m appearing everywhere. So what we obtain in the end for the mean field control is that we are going to have an ODE for the mean. So I will denote it by z check. We have a control. So again, I use the notation alpha hat for the Nash equilibrium, and I use the notation alpha star for the social optimum to distinguish. So here we have an expression for alpha star. And you see, it looks exactly like before. So you could say, well, I mean, the optimal control is going to be the same because it's minus b over c, p x plus r. But the thing is that p and r are going to solve different ODEs than the one we had before. And the value is not u, it has a more complicated expression. So maybe I will skip this for now, but you can express the value of the cost. And how do you express it? Well, you really have to take the total cost. So you go back to the definition and you define the total cost by taking the integral between 0 and t of the integral of the running cost multiplied by m at time t dx plus at terminal time the integral of the terminal cost multiplied by gt dx. And here you have to take m controlled by alpha star, m controlled by alpha star, and you have expressions for m, for g. You will realize that these integrals simplify to just the mean, and then you can finish the computation, and you get something which is more complicated than just u at time 0. And this is because u is the adjoint state and not the value function. Sorry, I see there is a question or comment. So thank you. So the question is, what intuition is behind the ansatz for you? So yes, very good question. Thank you. I just threw it at you. So let me go back here. Maybe in the case of midfield game. So okay, one possible answer is this is a standard trick in optimal control, and we use this trick. So it doesn't come from midfield game somehow. Maybe one possible intuition is that if you look at this expression, the first thing is that it's going to involve. You see that it's involving x squared and x here, but you realize that in the PDE itself you have only a polynomial of degree 2 in x. So maybe that's one reason why people thought about introducing this ansatz for u, because you see that if you take u of this form, when you compute the partial derivative, you still end up with polynomials of degrees at most 2. So for the time derivative, it's still of degree 2, and otherwise it's of lower degree. And then when you plug everything in the PDE, you have a big polynomial of degree 2 with unknown coefficients. And you would like this polynomial to be equal to 0 for every x. And then this helps you to find the coefficients. So I think the idea is by looking at the PDE, seeing that it involves only x and x squared, and then taking a guess that the value function would be of a polynomial of degree 2 as well. Thank you. All right, so let's see. We are almost done with midfield control, and then we can discuss algorithms. So for midfield control, then you apply the same strategy once you computed this term, which is a bit special, and you can compute it with the terminal cost as well. And after that, you go back to your AJB, you plug everything, you identify the terms of order 2, order 1, order 0, and you get ODEs for P, R, and S. Sorry, there should be a check here because it's F check. And you have similarly a forward-backward system. I put in purple the extra terms, and you see that these extra terms affect only the backward equation. And in fact, here they affect only one of the 3 backward equations, right? You have 3 backward equations, 3 backward ODEs, and these extra terms coming from the derivative of the Hamiltonian affect only the ODE for R. So now, just a few remarks. So linear quadratic models are quite useful because the solutions are almost analytical. So I will come back to this a bit later. The model I considered in these notes is inspired by Bensoussan et al. So you can check the book if you want to have more details on the derivation. You can have much more general linear quadratic midfield games. So there are many references. I give just a few of them, but really you can include more terms. You can have interaction through the action mean, not just the state mean or the average of the state. You can have common noise, etc., etc. In some cases, with a different model and using a different ansatz, you can manage to completely decouple the ODEs. So here, if I go back, the ODEs are coupled. Why? Because if you look at the forward ODE, which is for Z, this variable Z appears here, and it also appears here and here. But in particular, it appears in the ODE for R, and you see that the R variable in turns appears in the ODE for Z, sorry. So you need Z, you need R for the ODE for Z, and you need Z for the ODE for R. And so you have a coupled forward-backward system. In some cases, you can manage to decouple. And the idea is to use a slightly different ansatz. For example, you could try to use an ansatz of the form x minus m bar squared, maybe multiplied by some coefficient C1 plus a coefficient C2 times x minus m bar, and then plus a coefficient C3. So maybe you can look for a polynomial in x minus m bar, and then you can manage to decouple. So here, the notes of Roland Malamé and Christy Graves in the AMS 20 mini course lecture notes give more details on this approach. But as far as I know, it's not completely general. In general, you cannot decouple the forward-backward system. The equation for P can be solved by itself. So let me go back. You see that the equation for P, let me put it in green, this one does not depend on, and also the terminal condition, does not involve any other variable. So this one, I can solve it first. And it is a Riccati equation. In some cases, it even has a completely explicit solution, really an analytical formula. So I think I give the reference here. If you look at the book of Ramona and Delarue, page 110, there is a formula for Riccati equation. I'm sure it's not the only reference, but at least it is there. So when you want to solve a Riccati equation, under some assumptions, sometimes you have an explicit solution. The ODE for S depends on all the other variables. You see, it depends on R, it depends on Z, and then depends on P. It also involves P. So for S, you need everything, but S is not involved in any of the other equations, so we can solve it last. So the key point is really to solve the equations for Z and R, because they are completely coupled. And I will focus on this to discuss algorithms. Z and R. So let's see. Maybe it is a good point to take a short break, but maybe really short, so we don't spend too much time. Maybe just 4 minutes. How about we resume at what is it, 2:40 in local time? So if this works for everyone, maybe just 3-4 minutes of break.
I think should be okay. Mathieu? I would like just to take 1 second to tell everybody, please check the chat zone to get the code for the attendance certificate. Thank you.
All right, so maybe we can restart now. And so what did we do so far? So I recalled the mean-field game PDE system, discussed the mean-field control PDE system, and the intuition behind mean-field control, the difference between the two types of problems. And then we looked at the linear quadratic setting, and we derived systems of ODEs, both for mean-field game and for mean-field control. And what I would like to do now is to present algorithms to solve the forward-backward system. And most of these algorithms can be used later on in the PDE system, what we are going to discuss in the next lecture. So I think these ideas are quite useful in general for mean-field games, at least. And so I will revisit some of them later on throughout the future lectures. And at the end of this section 3, I would like to show some code and some numerical simulation to produce the plots that I'm going to present. So the experiments are described in more details in the notes I mentioned earlier for the AMS short course in section 2. So we focus on Z and R because, as I said before, P we can solve a priori, S we can solve a posteriori. So we focus on this fully coupled system for Z and R. It's an ODE system, so I will focus on the one-dimensional case. So Z is a one-dimensional function of time, and Z is and R is also a one-dimensional function of time. But we cannot plug that directly in a computer, a function of time. So we need to have a finite dimensional approximation. And here what I'm going to do is I'm going to replace the time, continuous time, by a grid. So I discretize time, little n between 0 and, let's say, nt time steps. And delta t is the size of one time step. I will use the notation capital Z and capital R for the vectors in time. So as many dimensions as time steps. So here, you can propose several approximations. Here I'm using this one. So you see that for Z, Z is the forward variable, and I'm going to use an implicit scheme because I put Z at time n+1 on the left and on the right. And similarly for for R, which starts at time nt, it's backward in time. I am going to use Rn here and Rn here. So it is implicit for R as well. It is an implicit scheme because it goes backward in time. So now we have, so let's see, we have how many equations? So we should have nt+1 equations here and nt+1 equations here, and we have 2 times nt+1 variables to compute. I will describe the algorithms, except for Newton method. I will describe the algorithms using the continuous time ODEs, but basically when we want to implement, we use these discrete time finite difference equations. So I will start with fixed point iterations, and then I will present variations of this fixed point, and I will also discuss Newton method. So fixed point iterations, the idea is pretty straightforward. So you start with an initial guess. So you initialize Z superscript 0 and R superscript 0. So the superscript is for the iteration. So when I will write, for example, K like this, it means iteration K of the algorithm. And here I write R as a function of time, but think about the vector, discrete vector in time, I mean, discrete function of time. And so what you do is, given the current guess for Z, so for example, take K is equal to 0, you solve this ODE where everything is already known. And what you do is you obtain R at iteration 1. So if I plug Z at iteration 0 here and here, I solve the ODE backward in time, and I get R1 for the first iteration. Then I take this R1 and I plug it in the ODE for Z, which is for the forward equation. And in this way, I get Z1. So the result of one iteration is that I get a new R and a new Z, and I can repeat this process. This amounts to say that I'm really solving the backward equation, then solving the forward equation, solving backward, etc., until hopefully this pair here is a fixed point. I'm hoping to find a fixed point for the forward-backward system after iterating many times. I hope this makes sense. Otherwise, feel free to ask a question. Here, I'm noticing, sorry, this should be a lowercase p because capital P is for the vector, but anyway, lowercase p is for the function of time. But in practice, I use vectors because I discretize. So I'm going to show this, but on the first example, here is what we see. So I need to describe the plots. You choose some values for A bar, Q bar, etc. All the parameters, you fix their value, and then you apply this algorithm, and you see what happens. So the plot on the top is describing the difference between 2 iterates. So in other words, this is the difference between one iteration and what I get at the next iteration. And this difference should go to 0 if I have a fixed point, because if I have a fixed point, it means that between one iteration and the next one, there is no change at all. So we see that here the x-axis is the iteration number. And at the beginning, the difference between 2 iterates is not negligible. But after a few iterations, here just 10 iterations, basically, the value is pretty small. It's not 0, but numerically it is small. And maybe the error that remains here is due to the fact that we have a time discretization and I'm not really solving the pure ODEs numerically. So it seems that here it is converging. And if I plot the solution, now Z is a function of time, R is a function of time. And here I use time as the x-axis. And I see this plot, and I'm not going to try to interpret it, but this is the result, Z as a function of time and R as a function of time. So in this case, a fixed point algorithm works well, at least from a numerical point of view. But there are some cases, if you change a bit the values of the parameters, A bar, etc., there are some cases where what you see in terms of iterations is that the distance between two iterates keep increasing. So in fact, it is basically diverging in some sense. And if you look at two successive iterations, you see, for example, I don't remember the exact number, but let's say this is k is equal to, for example, 3, and this is k is equal to 4. And this will be, you will see something similar when you go to k is equal to 5 and k is equal to 6. So what is happening is basically that you are oscillating between two solutions. This is not completely true because you see that the distance between two iterates is not constant, it's actually increasing, so things are getting worse. But the idea is really that you are oscillating between two situations. So here you see Z is decreasing and then Z is increasing. And so intuitively, what this means is maybe something like when Z is decreasing, everyone is trying to maybe go in the other direction, and then Z is going up, and then Z is going down. And so people don't manage to agree in some sense. And you are stuck in a kind of a cycle, or worse than a cycle, because the distance increases. So this is a case where a fixed point fails to converge. In fact, these fixed point iterations are very related, as I mentioned before, they are very related to the proof technique for existence and even uniqueness by using Banach fixed point theorem. And this goes back to actually the first paper of Huang, Keynes, and Malamé on this topic, where they really show the existence and uniqueness of a solution using a strict contraction. And so you have conditions for the strict contraction to be true. And if the conditions are not satisfied, then typically it fails. The algorithm also fails to converge. In general, the conditions are that you need a small time horizon, or you need some coefficients to be small enough in the definition of the problem, in particular the coefficients related to the mean field terms. And this is because you want a strict contraction, so at some point you need a constant to be smaller than 1. So then what is this constant? It depends on your model, but usually taking time small or taking the coefficient small help to make the constant smaller than 1. So next question is, can we fix this algorithm if it does not converge? If you see this kind of behavior, okay, so it's a good idea to try this fixed point algorithm. If you want to solve a mean field game, try this first. If it works, it will converge very fast, maybe just a few iterations. But if it doesn't work, then what do we do? There are several ideas, but probably the simplest one is to try to slow down the iterations and to try to prevent this kind of oscillations between different solutions, or not solutions, actually, to try to avoid the oscillations between bad behaviors, which are not solutions. Because let me go back just to clarify, I'm not saying that the one on the left is a Nash equilibrium and the one on the right is a Nash equilibrium. This is just oscillating between behaviors which are not Nash equilibria, and you just don't manage to converge towards the Nash equilibrium, which exists in this case. So there is a question by Amal. Hi, Amal. So is there any theory to estimate how small t should be to ensure convergence? Yes, in some sense. So I didn't go into the details, but when you do the analysis for a specific model, you end up with specific conditions. So let me write this explicitly. Basically, what you are going to do is you are going to say that you are going to say what? So something like, there are different ways to phrase it. But for example, if you give me R and you give me R prime, what I can do is, so I can view this step as z as a function of rk, because basically you give me rk and I define zk plus 1 as a function of rk. So now what I can do is I can take z of r and I can take z of r prime and I can try to compare them. I can try to compare them and bound these by the difference of r minus r prime. And here, so you take some norm, maybe the sup norm, for example, and you want this constant to be smaller than 1 strictly in order to have a strict contraction. And here, this constant is going to depend on t, is going to depend on a bar, etc., etc. So you get more or less explicit constants, but you can get an upper bound, and then if you ask that this upper bound is strictly smaller than 1, you can ensure contraction. So in some cases, you get almost explicit conditions. These are sufficient conditions, maybe not necessary. So that's why I'm careful about my claims. I'm trying to be careful, but these are sufficient conditions in order to get convergence. All right, so we can use damped fixed point iterations. So the idea is to say, well, maybe people are somehow reacting, somehow people are overreacting. So let's imagine that you are driving to your, or you are walking to your, I don't know, favorite place, and you observe the crowd on the way. So maybe it takes a very long time to go. Then the next day you say, well, I'm going to use a different path. I'm going to take a different path. But if everyone's thinking that way, then the next day everyone uses this other path. And so the following day, everyone changes again, and you are always in a situation where it's crowded and you are never happy. And so it's never a Nash equilibrium. The Nash equilibrium in that situation would be to choose randomly either of the two paths. And if everyone does that, then you end up with maybe half of the population on one path, half of the population on the other path. And this would be maybe more optimal. So what I have in mind is maybe you have an origin, you have a destination, you have two possible paths. And somehow, if you want to decrease congestion, you would like to have, I mean, the Nash equilibrium would be to have half of the population on each path. But you are not going to reach that if you overreact somehow each day to the other situation. So damping the iterations can be a way to ensure convergence. So here, I will describe damping on Z, and the idea is the following. So I solve the backward equation, so I get RK plus 1. Then I plug it here. I solve the forward equation, so I get zk plus 1. But I don't plug immediately zk plus 1 back here. What I do is one extra step where I average. So I do a kind of moving average between zk plus 1 that I just computed and a moving average coming from previous iterations. So z tilde is a moving average. And you see, this is exactly what I plug in this ODE. It is some kind of average quantity over past iterations with some multiplicative factor delta and 1 minus delta here. So I will call that damping, but you can, there are certainly many other ways to name this algorithm. So it turns out that this brings some stability, and in the same previous example, if I use damping of 0.1, then it converges. So you see that the distance between two iterates decreases. We need to be a little bit careful because sometimes the distance between two iterates is not really a sufficient criterion for convergence. But here, if I have a constant damping, it's a sufficient criterion for convergence. All right. If I use a smaller damping 0.01. So delta equals 0.01. So let me go back here. Whoops. You have delta times z tilde k plus 1 minus delta times zk plus 1. So if I take delta 0.1 or if I take delta 0.01, so here this would be 0.9 or 0.99. You see in the first case, I give more weight to the previous update, to the previous iterate, than in the second case. In the second case, I give very, very little weight to the previous updates. And if I put delta is equal to 0, I am back to a pure fixed point. So when I use delta equals 0.1, it converges. When I use delta equals 0.01, it does not converge. And then when I use delta equal to 0, I already said it didn't converge. So you see the choice of the damping can help convergence. And depending on how you choose it, it may or may not converge. So the value of delta is important. Of course, if you choose a large delta, you are going to slow down a lot the convergence, because imagine that now I put 0.9 here and 0.1 here. Of course, it means that the new update, zk plus 1, has a weight 0.1, which is quite small. So you are going to slow down a lot the convergence. Maybe it is necessary in order to get convergence, or maybe not. So if you can use a small delta, it is better because it will go faster. But sometimes you need to put a large damping coefficient. Fictitious play is another instance. I mean, I like to see it as another instance of damped fixed point iterations, although it's not completely true, because historically, I think it's maybe the origin is different, but it was introduced by Brown and analyzed by Robinson. So this paper of Julia Robinson is in the Annals of Mathematics. So game theory and fictitious play and learning in games is really mathematics. It's not, now it has been maybe really more studied in computer science, but there are a lot of beautiful mathematical questions in these algorithms to understand the behavior of the algorithms. So convergence in several settings and extension to the mean-free game case, in particular by Kardelia Gay and Hadi Kanu, and then follow-up works. Typically, it converges when you have a monotone mean-free games, meaning a mean-free game with a cost which is monotone in the sense I have described in the first lecture. So potential, for example, but it can be beyond the potential case. And so fictitious play has also been studied in the case of, in the situation of model-free reinforcement learning. I will come back to this in lecture 6, the last one. The idea is that you take a special choice of damping. Let me just zoom in here. You see that instead of taking a constant delta, you take a delta which depends on k, and which is of the form k over k plus 1. So this is delta, but it is a function of k now. So you can let delta depend on the iteration number. Here let me put this between quotes just to say that maybe it's not the traditional fictitious play. I'm just using this ODE system as an illustration and using the same coefficient, k over k plus 1, as in standard fictitious play. But I'm not sure if it has really the same interpretation, as we will see later when we really do fictitious play for the PDE system or for the forward-backward system with the distribution. Here, the behavior that we see is somehow convergence, very smooth, but very slow, right? So you see that it decreases, at least it's not increasing and diverging. However, the evolution is slow, and it is getting slower and slower. And intuitively, it makes sense because the damping coefficient is increasing with k. So as k increases, okay, as the iteration increases, delta k also increases. So if delta k increases, it means I slow down more and more each iteration. And at the end, after iteration 200, it means basically that I have 200 over 201 of z tilde k. plus 1 over 201 of z no tilde z k plus 1. So the new update has a weight 1 over 201. So you see, in this case, looking at the difference between two iterates, I cannot expect a difference bigger than something proportional to 1 over 200, because anyways, the updates are very small. So here I just recast everything in a common framework by writing delta as a function of k. Pure fixed point is the case where delta k is equal to 0, and fictitious play is the case where delta k is equal to k over k plus 1, at least what I call fictitious play in these slides. We could put the damping on R instead of Z, and you get a pretty similar result, at least from the point of view of numerical experiments. Shooting method, I will not discuss it, and I didn't implement it in the code I'm going to show next. The idea is to say that you have a forward-backward system with a terminal condition. What you could do, what is really annoying, is to have this forward-backward structure. So why not just writing two forward equations where the starting point of this one is unknown? Because in the end, if you solve this forward-backward system, it's true that R has some value at time 0. It's just that the value is unknown, right? So what I could try to do is I could try to say, I'm going to fix R0, Z0 is given, then I solve the forward system. And if the terminal condition is not satisfied, well, I pay a penalty and I try to minimize this penalty until I find the correct R0. And this is what I would call a shooting method. Again, I'm not going to illustrate it here, but it will be useful when we discuss later deep learning methods for forward-backward SDEs. At some point, we are going to see a shooting method like this. Okay, we are almost done with the algorithms. Newton method is the last one I want to present. So what is Newton method in dimension 1? Just a reminder, it's a method to find a root of a function. So we want to find x star such that f of x star is equal to 0, starting from some initial guess. And the update is xk plus 1 equals xk minus f evaluated at xk divided by f prime divided by xk. I'm not going to say anything about this algorithm. In general, you can prove a kind of local convergence result, meaning if you start close enough to the root, you are going to converge to the root. In high dimension, we try to avoid computing the inverse of f prime. So f prime would be the Jacobian of the function. It would be a matrix, and computing the inverse of a matrix is expensive in high dimension. So what we do is usually we use a small trick. We solve a linear system, this one. We find the solution x tilde k. So remember that xk is known here. So I can compute f of xk, I can compute f prime of xk. I solve this linear system, I get x tilde k, and x tilde k has exactly the interpretation of this quantity. So I can add it to xk and get xk plus 1. What else can I say on this method? The Jacobian f prime of xk usually is something that we are going to compute by hand to save time, because I know the function f for which I'm trying to find a root. So usually I can compute the Jacobian by hand and then implement it directly instead of doing other computations. So here, what is the link with what we are trying to do? Well, remember, we have this forward-backward system for Z, so for R and Z. So here now I'm going to use the finite difference version. So you have Zn, I think I had put the n here, divided by delta t, and you have also Rn plus 1 minus Rn divided by delta t. And we had this forward-backward system, but basically we have a system with 2 times nt plus 1, if I take also into account the initial and terminal conditions, 2 times nt plus 1 equations. So I can define a function f, which takes these 2 vectors and which is 0. This 0 is in dimension 2 times nt plus 1. And it encodes all the equations I want to solve. So I will leave it as an exercise to express f and to express df, so the differential of this operator. Actually, you can see their form in the code, but here you can try to complete this exercise on paper and try to compute f and df, again, for this forward-backward system for z and r. Now, Newton method is just finding a root of f. We want to find a root of f, except that what I was denoting before, x k, okay, this xk now consists of the pair zk and rk, which is in dimension r times 2 nt plus 1. And then we apply Newton's method. So here we solve the linear system I mentioned before, and then we add this x tilde k plus 1 here, or x tilde k, depending on the notation. So this is a method to find the root, and you see that here we don't, so here we do not exploit the forward-backward structure. So this is a key difference with the previous methods. I take my forward-backward system, I define some operator for this system, I look for a root, and at once, somehow. So there is no forward-backward iterations. When I say I don't exploit, maybe the structure, of course, is still here. It is hidden in the definition of f, but I mean there is no forward-backward iteration. So it's really a kind of different method. If we look at this method, here is a result that I get, and it's true. I will show you the numerical results later. If you look at the x-axis for the iteration number, you see that there are only two values, 1 and 2, and you get an error of 10 to the minus 13 between two iterates, meaning it has converged almost exactly. So you could say, well, maybe there is something wrong because the algorithm converges in one iteration, basically. So how is it possible? It's kind of magic, but it is possible. So I don't know if there is any guess about why this happens. But the idea is the following. The explanation is the following. So here is the forward-backward system that we have. And we can rewrite this system as, in fact, a linear system of equations. So if you look carefully at this system, you can define some matrix M, multiply the vector ZR. So let's imagine I concatenate all the time steps for Z and then all the time steps for R. I end up with a long vector. I add a vector B, and this is the system I want to solve. I want to find ZR that solves this linear system. And actually, in this situation, for a linear function, Newton's method converges in one iteration. It's true, even in dimension 1, you can check it, that Newton's method converges in just one iteration. In fact, in hindsight, once you see things like that, computing Z and R is just solving a linear system, this system here. So I don't need any forward-backward iteration. I don't even need Newton method. I just need to solve a system of linear equations. So I need a solver for linear equations. So everything I presented so far, the algorithms were really for the sake of illustration. The bottom line is, if you want to solve this ODE system, don't use fixed point or fictitious play or this kind of algorithms. Just use a linear solver. When we are going to discuss PDEs, the equations are going to be nonlinear. And so for nonlinear equations, it becomes justified to use more sophisticated algorithms like fictitious play or like Newton's method. So that's why I wanted to present these methods. Briefly, MFC. So I already mentioned that the price of anarchy is the cost of mean field game divided by the cost of mean field control, meaning it is the average cost that the player gets in a mean field game versus the average cost a player gets in a mean field control. And the denominator is always smaller. In some cases, they are equal, but not always. And in this paper of Carmona et al., there are some explicit computations for linear quadratic mean field games for the price of anarchy, explicit or maybe some asymptotic result when some parameters tend to some value, they manage to get bounds on the price of anarchy. Here, I just do some numerical computation. You can solve the forward-backward ODE system for mean field control in the same way that the one for mean field game. And then you can compute the price of anarchy, and you can play with, for example, the influence of A bar, the influence of Q bar, and other parameters. Here, what we seem to see, although the values are pretty small, is that when you increase A bar or when you increase Q bar, the price of anarchy increases. And I think this makes sense because when A bar or Q bar increases, it means that the mean field interactions have more impact. So if the mean field interactions have more impact, somehow you should see a bigger difference between mean field game and mean field control, between the cooperative and the non-cooperative scenario. Whereas when A bar and Q bar would be equal to 0, if all the terms with bar, so for mean field interactions are 0, then there is no mean field interactions at all, and then there is no price of anarchy. It should be equal to 1 because you don't interact at all with other people. So here I will show a Python code to solve the mean field game as forward-backward ODE system. And I will leave it as an exercise to do the mean field control. So you can download this code and you can modify it and try to do the computation from mean field control and also compute the price of anarchy once you have the mean field game and mean field control. And what I have after that, let's see, we have 15 minutes. So maybe I can briefly go through the next slides and then we look at the code. I will share my computer screen. So I have just a few slides preview for the numerical schemes of the PDE system. So in the PDE case, you have a forward-backward system. We are going to need two things. One is the numerical scheme, which is about how to discretize the PDE system. And I already mentioned that discretizing PDEs is not so trivial if you want to respect some properties. And the second thing is, once we have a discrete system, we want to solve this discrete system. And here we can use a bunch of different algorithms. For example, the ones I've presented here. So in fact, when I talk about numerical methods, there are really two components, the discretization or the approximation, and then the algorithm itself. Some properties we are going to want to preserve, mass positivity, convergence of a discrete solution to a continuous solution, and also some kind of adjoint structure between the KFP and the AGP equation. So we need a careful discretization, and the computation of a solution can be done in a way similar to what I've presented before. So I'm mostly going to focus on two numerical schemes, at least for PDEs. A finite difference scheme by Ajdu and Capuzzo-Zurcheta and Camilli and others, and a semi-Lagrangian scheme introduced by Carlini and Silva, and then there are several follow-up papers. There are other options, for example, finite elements, but I will not have time to discuss that here. So I will do that in the next lecture tomorrow morning, and I will also discuss methods for FBSDs. Let me skip this and let me show you the code since we still have minutes. But if there are any questions, feel free to ask me as well. While I pull out the code. Okay. Sorry, I was not supposed to do that. I'm supposed to share my screen. All right. So I think you can see this. So if you download my slides, which are on my webpage, and you click on the link, you should be able to see this code. So the code is in Python. In fact, it is in a Python notebook. And so here, for the sake of illustration, I am going to use Colab, which is a service provided by Google, where you can run codes for free up to some limitations in terms of compute power, etc. And so I'm going to use that for the sake of simplicity, but you don't have to use that. You can download the Python notebook and run it on your computer. You need Python and Jupyter. So here I'm going to just show you. I connect to a runtime. Then this code has some imports. So I will skip this. Here I define the parameters. So you see the parameters for the model, DT, etc. Then I prepare the solver. So after I prepare the solver, I can run several algorithms, and then I have a few illustrations. So here, let me run it. You see that, for example, I solve the ODE for P here with these few lines of code. So P is actually the P is a backward variable, is one of the three backward variables. We can solve it a priori. Z is the mean. We can solve it forward, but to solve Z, we need P, so we will pre-compute it, and we need R here. So R is going to be coupled with Z, and we are going to need iterations between the two. So this is the ODE for R. You see, I have a few lines of code. I skip the details, but you can take a look if you are interested. This is the ODE for R. Remember that the ODE for R is the one that differs when you want to do MFC. So here I leave it as an exercise. For R, you need to change these coefficients here for MFC. And then the zeroth order coefficient in the value function, which was called S. And this one, you solve it a posteriori. Once you have Z, P, and R, you can compute S. Now, I have this solver. I call it solver pcar because it's basically pcar iterations or fixed point iterations. And it will take as a parameter a damping function. So this is my delta K in the nodes. And it can be 0. It can be, by default, it will be 0, but it can be a constant. It can be a function of K, for example, for fictitious play. So I will recover as an instance of this algorithm, pure fixed point, damped fixed point, and fictitious play. So here you see there is a loop, and in this loop, I keep updating Z and R by solving the ODEs. And actually, the really useful lines of codes are these ones. And after that, it's mostly about printing and plotting. So you can hide this, and basically the algorithm is very short. It's just about solving the ODEs iteratively. Then I have a function to compute the cost. In the mean field game case, the cost is just U0 times M0. But in the mean field control case, the expression is more complicated. So here, exercise, you can compute the cost in the mean field control scenario. So then you can run these examples. Here, this is basically test case 1. So I already ran it for you. And you see that at the beginning, so it prints every 10 iterations, a plot of the convergence, the difference between two iterations, the shape of Z and R. And here you see it converges. Pure fixed point iterations converge. I use a damping of 0 and it works. However, if I change the parameter, so let me hide this. If I change the parameter and I put, for example, A bar equals 2.45 instead of 1, meaning that I increase the influence of the mean field term in the dynamics. Remember that A bar is how much the mean affects the drift. If I do that, and I run again here, I think you are going to see something that diverges. So in the meantime, there is a question, could we use mean-field game for any game theory? I don't think so, because in mean-field games, in order to get a mean-field game, we make some assumptions, in particular that the population is homogeneous, and they interact only through some aggregate quantity. So if you take, for example, a two-player game, I don't see how you can do a mean-field approximation. Or if you take a game where all the players are completely different, as they have different cost function, different dynamics, etc., I don't think you can use a mean-field game in general. But there is some regime where the mean-field approximation can be useful. So here, what we see is that the distance, as I already shown in the slide, the distance between two iterates increases when k increases. And you see, for example, here, I have z at iteration k and z at iteration k plus 1. Let's say z old is maybe zk minus 1, and this is zk. And you see it oscillates between 2. But if you look at the y-axis, it actually increases. So this means that the solution gets bigger and bigger, and the effects are kind of increasing. So let me stop this now, because it's going to diverge anyway. And here now I use a case of damping 0.01. So when I put a damping constant 0.01, still it does not manage to converge. You see it increases slowly, but surely it increases, and so it does not manage to converge to a fixed point. If I increase the damping 0.1 here, then now it converges. So I didn't change anything in the model. It is the same mean-field game, same parameters, same forward-backward ODE system. The only thing I changed is the algorithm by introducing a little bit more of damping. So really changing the algorithm helps you to find a fixed point, actually, or at least an approximate fixed point. So one thing you can try is it possible to get below 10 to the minus 5? I suspect these oscillations are due to numerical errors, but maybe you can try to refine the mesh and get an even smaller error. Then I call this function get cost, and this computes the total cost, and it also outputs P, R, and S at time 0. So here you have a cost of 3.26. I don't have a specific interpretation of the cost in this setting. Okay, this linear quadratic setting is just for illustration. You can use linear quadratic models with some specific interpretation in mind, but here the linear quadratic model I'm taking is just for mathematical purposes. So I don't have an interpretation of this cost, but you can study how it increases or decreases when you change some of the parameters. Fictitious play. So here you take a damping function, which is the index of iteration divided by the index of iteration plus 1. And you use the same algorithm, solver Picard, but with this damping function that I've defined above, and you get the kind of plot I've shown earlier. You see that it converges. It seems to converge, but very slowly. Newton iteration. So this one is of a different type. Here I need to define the operator f and the df, the derivative of f. So here, this is the part where I said I pre-compute by hand the derivative of f, which can be cumbersome. But if you do it, then you save computational time. So the key point is to not mistake when you define f, and to not mistake when you compute df. Here I use sparse matrices because the matrix for df is going to be mostly sparse, and I don't want to have a huge matrix full of zeros. So in practice, using sparse matrices is a good idea. I will skip the computation because this was one of the exercises in the slides, but you can take a look. And then I define one step of Newton, which is really what I described in the slides by taking the temporary x and then adding the temporary x to x old. So xTMP was x tilde in the slides. After that, the solver consists just in repeating updates of Newton steps, and you see that it converges in just one iteration. So you can redo the test and see it converges in just one iteration. Here I compute again the MFG cost. So you see it's pretty much the same because it has computed the same solution. This one should be even better. And then once you realize that, if you want to study the influence, for example, of some parameters, for example, the influence of Q bar. So what you can do is you let the value of Q bar vary, and for each value of Q bar, you solve the mean-free game, and you compute the cost, because now you have everything. And to solve the mean-free game, it's probably better to use Newton because it converges in one iteration, or to use a linear solver so that it goes very, very quickly. For each value of Qt, you compute the cost, or Q bar t, you compute the cost, and you see that, let's see, this is the steps for Newton, but at the end, I have different values for Q bar t, and I have different values for the cost. So you can see that the cost changes when I change Q bar t. And you can do the same thing for A bar, same thing for Qt. If you do the exercise and you implement the code for mean field control, you can similarly compute the cost for different values of Q bar t, A bar, and Qt. And then you take the ratio and you get in this way the price of anarchy. So this is how I got the plots for the price of anarchy. That's it for the code. So you can download it, play with it. Please let me know if you have comments or questions. I would be happy to have feedback. And I don't know if there are further questions. Otherwise, I will just stop here and thank you for your attention. And thank you for all the reactions in the chat. I appreciate your feedback.
Are there any questions from the audience? If no, please notice that the code for the attendance for this afternoon is not the same as this morning. I will give it back in the chat. Okay, and okay, I let Francois close the session.
Okay, thank you, Mathieu. Thank you a lot for your lectures. So tomorrow we are back at so this is 9 a.m. UTC +1, so in Morocco, and 10 a.m. in France, and so on the same schedule as this morning. I don't know if you have any questions on the organization for tomorrow. No question. So maybe we can meet again tomorrow, same link and same schedule as today.
Okay. Thank you very much.
Thank you, Francois.
Thank you to you.